And it's a star ADC actually. It's a star block. So remember, in the star ADC, we need a clock for the ADC itself, for sample and hold, for conversion. So the thing is, we don't have an external clock for this guy, right? So where's the clock? The question is, where's the clock? And this schematic is even missing the clock signal. So it has more errors actually. But I searched a couple times on Google. I just couldn't see an official schematic of the PMOD we have. It's the only one available. So I'll probably have to draw it myself in the future. But anyway, but if you look at this one, you do need a clock, right? So the ADC chip, this ADC's data sheet, this one doesn't lie. Usually the data sheet has everything on it. Right? So the VIN is actually the voltage input from the light sensor. And you got a chip select, you got a IS data. So IS data is which pin on your PMOD sensor? Could you take a look at it? Take a look at it. IS data pin is which pin on your sensor module? Light sensor module? What's that called?
Is it the ALS?
Yeah. Yeah, because it's basically just the ADC on it, right? Just ADC on it. And the light sensor is the light sensor signal goes to VIN. And the output of the ADC is not going to anywhere but the ports of the PMOD module. So ICK is what? No, ICLK is what? ICLK definitely will be SCK, right? It's directly just SCK. So CS will be SS. SDA, S data is SDO. Okay? So this one is not taking anything in. It's just outputting to leader, right? To the leader device. So this is actually SDO. This is SDO. And it's very interesting ADC because the lower 4 bits is just zeros for the data output. I don't know why, but it's just how that was designed. So the lower 4 bits are zeros whenever there's a digital analog VIN shows up at VIN. It starts doing the sample and hold, right? So sample and hold it, and then starts conversion. So the conversion takes up to 16 clock cycles. Keep in mind, okay, 16 clock cycles. And that clock is basically your SCK of the SPI. All right, and SCK of SPI is defined by what? By the leader, right? By the IPGA. Could you just go recall that when you talk about it on Tuesday? We are looking at what? Leader receiver, leader transmitter, follower receiver, follower. Which one we are looking at? Leader receiver, leader transmitter, follower receiver, follower transmitter. Which one we are looking at?
Leader follower.
No. Leader follower? Receiver transmitter? It's impossible, right? So the leader receiver or leader transmitter or follower receiver or follower transmitter, right? Which one we are looking at for our IPGA for this project? Is IPGA reading or writing? Reading, because it's receiving data from the light sensor, right? So the light sensor is a follower, but it's a transmitter as well, right? So your leader becomes what? Receiver. It's a leader receiver. So we're looking at the leader receiver module of the IPGA. Does that make sense? Okay. So now we come down to leader receiver. Okay. And we already went through this on Tuesday, but let's just review this really quick. You can see that we have a positive edge of the clock, which is not doing anything but just defining the clock, right? So your IPGA actually defines the clock. You are not seeing anything on the ADC board or the PMOD sensor light sensor module. It doesn't have a clock, so the clock comes from your IPGA's code. So whatever you write into IPGA, you synthesize it and implement it onto IPGA, and that one will provide ICK for both. Okay? Don't imagine that there will be a magical clock coming from anywhere. If you put a 25 over here, it's going to create a 2 megahertz clock for your ADC. Okay, so this guy is going to drive your ADC's clock and do all the conversions. And you need 16 clock cycles to complete one data conversion. So which means based on the frequency over here, whatever you design in the system for the communication, it runs 16 cycles to get one data out. So my question for you guys is, what's the sampling rate? So sampling rate, I'm talking about samples per second, SPS, not BPS, right? SPS. And a lot of times you'll see papers, titles, blah blah, whatever ADC design at a frequency of KSPS. What does that mean? KSPS. Kilosamples per second, right? So keep in mind, for the ADCs, we talk about SPS a lot. So samples per second is a lot of times something we care about. So it's one of the questions on the in-class. I forgot which one that is. It's number 8, I think. Right, number 8. So given the range of the SPI's frequency to be what? What's the range of it? SPI 1 to 4 megahertz. Doesn't matter. It could be 5 megahertz. Doesn't matter. So let's just say SCK is 1 to 4 megahertz. Is the range, okay? It's 1 to 4 megahertz. What is the sampling frequency of your ADC? The range. What's the range of it?
1 to 4 megahertz over 16.
Yeah. So 1 megahertz divided by 16 will be the lowest, and 4 megahertz divided by 16 will be the highest. Okay. So now let's take a look at the code we have from the textbook. Here. So all these are given. You need to make certain changes to your top. I'm just showing you that this is the top module. And what you need for all these, for the design of this project, is that you need a top module, and name of the top module is available from the textbook. It's called SPI_licensor.v. And there's the SPI_leader receiver, which is available. Just directly use the ones we have. And there's another one called binary to BCD. It's the binary coded decimal. That's question number. That's in class number what? Number 10. In class 10. In class 10 and question number 11. How BCD works? Binary coded decimal, because the converted results from the ADC are digital numbers, and you want to convert it to decimal numbers and display them on the 7-segment display modules. So you want to separate the units or different digits, like at the 1,000, 100, and tens, and single digit as well. So you have a number, for example, it's 232, right? even though this is a decimal number, but it could be a binary number, right? Just imagine this is a binary number, its counterpart in binary. And if this one divided by 1,000, no, let's just write it in the Verilog operators. If I do a division, what I'm getting? 0. Right? So which means there's no digit at the 1,000 position here. And if I do a 232 divided by 100, I'm getting 2, right? So 2 is getting separated from the number. So I can throw this one to the 7-segment display. Gonna display a 2 here, right? Okay. And then if I do a 232, this is called modulus, right? It's modulus. I'm getting a remainder of the result. So what I'm getting here, $32. And I'm going to use this result to run a division, and I'm getting 3. So I'm displaying 3 here. Okay. And I'm using 32 to a modulus of 10. So the remainder is 2. You could directly throw 2 here, right? And I think that's what you should do actually. 2. And after all these operations, you are able to separate every single digit for the decimal numbers. And just throw them to the 7-segment display, so you can display the light intensity. And this is 8-bit resolution, so which means the maximum number of the light intensity would be what? 255. So expecting something from 0 to 255, right? So my question is one of the questions on the in class actually. Do you need to? It's jumping back and forth from the 2 in class. So it's question number, let's see. This is question number 6, right? It's asking you that if the THOS is necessary, which is the digit at the 1,000 position here, right? Is that needed? Of course it's not, because you only have 255 as the maximum number. Why do it divide by 1,000? So if you look at the example code here, you zoom in. So see all these modules, okay? Top, BCD converter, 7-segment display, and decoder of the 7-segment display, and then SPI. So these are all the modules we have. And I'm gonna just to show you guys these ones one by one here. So take a look at this one. That's a binary to BCD converter, right? And it does exactly the job we just described. And it's trying to separate these digits or these numbers for the decimal digits. Okay? Thousands, hundreds, tens, ones. And you can see the width of these ones are at 4 bits. So why they need a 4 bits? Why does it need a 4 bits for each?
Is it so like you can like represent the range in the numbers?
So what's the range?
0 to 9.
Yeah. Okay, so 3 bits can only represent up to 7, right? Because it's up to 9, so you have to use 4 bits. And for the binary number input, is taking up to 12 bits as an input. So that's actually the data. And then this start, you can see band rate is being sent, being assigned to the BCD data, and the BCD data is the number being used to divide 1,000. You got started is just start doing the conversion as what we described, right? So start doing all the divisions and getting all the remainders. So no matter what this data is, right, based on the 8-bit ADC's resolution, and this step is really unnecessary because you don't have anything at 1,000th position of the number, right? It doesn't have it. Its maximum number you can get is actually 255. You're not getting anything larger than that. So this is a sum module. It takes in a binary number and outputs these ones. You just think about that way. So the binary to BCD converter, it takes in that binary number and outputs the results. And these results are 4-bit results that are available for the lookup table for the 7/7 display. Remember, we have been checking that 4 digits, right? See what the 4 digits are, like the calculators we used. We code it digit, right? Whatever, the data, digit. And it's a 4-bit, we do the cases. If it's this case, we show this pattern. If it's this case, we show that pattern. So we, according to all the digits, the numbers, we show different patterns. And you can see that from here. All right. So these are the decoder. This is a decoder module for the 7/7 display. It takes in all these data and shows different patterns. And this is the driver. So they, instead of integrating everything into a display module like we did, so the display module is actually the one that I wrote, but the textbook has different strategies to show this data, right? So for example, this one, they separate it. They have a decoder here. It just simply takes the input and output a pattern. And they also have a driver. So what does driver do? What does the driver do? Just by taking a look at it really quick. Why we need a driver, right? So the driver instantiates 4 decoders. All right, 4 decoders. Why? So you have 4 digits on the 7 display. You have 4 units, right? Display units. So what this does is it have a dedicated decoder for each unit on the display, and it uses the different states to scan through all the ANs, right? So every single time you only activate one of them, and they define that as one state. So it's the left, right, which is the one on the most left hand side, and then the one next to it is called the mid left, and then mid right, and the last one is the right, so which is the one on the right hand side. So it's activating each one by controlling the state. So if this AN pattern is like this, it falls into this state. So it's not going to other states. So during this state, it shows only display seg2 to seg, right? Because all of them share the same data lines. It's one of the strategies. So once this is coded up, you don't have to change it. Just keep using these, right? Just use this one along with the decoder, which is fine. And then we come back to the light sensor module, and you look at how these are getting instantiated, and you can see the way how the example instantiated everything here. They used the method that was not recommended. So when we introduced this one at the very beginning of the semester, we said do not really use the positional association method. We instantiate that sub module. Because it's assumed that everyone knows really well of all the signal lines of all the sub modules. It does not have the dot something parenthesis something, right? It directly just shows all the signal lines in the parentheses. And one of the questions in class 11 asks you that it's question number 7 in class 11, number 11. So for positional association. All right, the signal lines over here in the parentheses are the signals from where? From the submodule being instantiated, or from the top?
Top module.
It's from the top, right? So that comes from the top. So when you look at these signals, actually when you code it up in the top, you write down all the top signals, and at the same time you open another window for the sub module to make certain connections to them, right? So the order matters, has to follow a certain order. Again, this is highly unrecommended. In the future, for self, please have the naming association or named association, which is definitely more readable. Okay. Anyway, we can see these ones, these signals from the top. So if you scroll up by looking at here, oh, another question. So these signal lines are from the top. Do they have to be ports? It's a really fundamental question. Just test you if you guys are still awake. Do they have to be the ports? Do they all have to be the ports? Are they all ports? No, they could be wires. We have done that before, right? Remember, they could be wires. So if you look at these signal lines are from the top, we just talked about that, right? So they are all from the top. So now we scroll up. So remember that we have get, data, SDK, SS. Do we really have these ones declared here? Yes, we should. But if you just look at the ports, since this is the top module, these ones are keywords in the constraint file. And this is also a keyword in the constraint file. However, are the three signals like this, are they keywords in the constraint file or not? No, they are not. What about clock? Yes, but these three are not. Okay. What would you do? Can I directly use it with the older constraint file? What do you prefer? These pins are not available in the constraint file. If you put in the ports, it won't be able to do it with IPGA, right? You're getting errors when you are trying to generate a bitstream file. What should you do? First step.
Would we just make a wire to them?
Make a wire to them? No, these has to show up in the constraint file actually. So whatever you're putting here has to be identified in the constraint file. But you don't have them, right? Then just change the name of the ports in the constraint file. But what are the ports you want to change? What are the ones you want to change? You don't know yet. Can you just change whatever you want and then just plug in your PMOD and make it work? No, because these are header pins. They have fixed locations. You plug in. Unless you use jumping wires to make certain connections. When you have more time than you need, right? Because spring break, I have tons of time to kill. Let's just make it more complicated than I have to. So we'll plug in, okay, by looking at I think that's the JB ports. Those are the JB ports you plug in. They have fixed locations. You cannot change it. It's starting from the first one, then it's getting aligned to all the JBs. So I have to find out what are the JB ports, what the JB ports are over here. Okay? And then go to the constraint file and change the name of it. For example, if this guy, let's look at it. So for example, SDO here, SDO is connected to, for example, JB5. I don't know, I'm just making it up. JB5, for example, right? So you need to go to the constraint file and find a JB5 and change the name of it. Change it to what? SDO. Change it to SDO. So which one do you prefer? Do you prefer change the names here to JB5, or you prefer change the constraint files names to to SDO? Which one do you prefer? Constraint file. right? So your Verilog code is readable, more readable. If you put a JB5, you don't even know what that is. You have to put a command line explaining like SDO is kind of blah blah blah, right? Kind of JB5. So it's better to change the constraint file to these readable names, right? So go to the constraint file and change it accordingly. This is something you have to change in order to duplicate the task 1 of the tutorial. And another thing you can see here is because these ports, see, I also have ports here in the top. I have thousands, hundreds, tens, and ones in the top. Okay. Because these are being assigned to assigned to the LEDs. That's something important. But what I want to say is, so this binary to BCD converter module. Remember we just talk about it really quick. Let's come back and take a second look at it. So remember, binary is the input, right? So the first argument is the input, and all these are outputs. Because what it does is just do the conversion, right? It converts the binary into all these digits, right? So come back here. See here? And there's a curly bracket. Put all things together as what? Input or output? Input. So these are the output, right? From the BCD converter to the top. So the top is actually taking these in and use them for display. And these ones are actually being sent into the sum module. It goes into it, right? Goes into it. And then you have the digits out. So these goes into it, and if you look at the BCD, how many digits are they? How many bits? How many bits are going in? 12. Is this 12? It has to be 12, right? It is 12. So the question is why we are taking the light sensor data from bit 5 to bit 12, the A bits, and use them as the lower A bits of the 12-bit data. I think we should separate that question into multiple questions, okay? So first, do we need a 12 bits? Do we need 12 bits? I mean, the BCD converter does have a 12 bits, right? So, but actually the data itself is only how many bits? 8 bits. It's an 8-bit resolution. It's only giving you 8 bits results, right? So you don't really need a 12 bits. So I think they designed it that way because whenever you synthesize and implement the hardware, a lot of times probably you are not able to change it unless you are trying to re-implement your hardware again. So it's just making it wider to be used for other ADCs, okay? But for this application, for this ADC we are going to use for this class, for this tutorial, we do not need 12 bits. We only need 8 bits. This is one of the questions in class number 11, I think, because it's one of the questions. Forgot which one. But anyway, so we don't need 8 bits. We don't need 12 bits. We only need 8 bits. So if we come back to the top, so basically this guy can be changed to 720, right? 720. It should work. So here, we don't really need 4 leading zeros to be concatenated to your 8-bit data because they're not being used. If you look at the top, they're trying to assemble that 12 bits for your BCD converter. And to do that, they have to assemble 4 zeros in front of the ADC data, right? It's just so silly, right? We just don't need it. We don't need it. So it's only 8 bits. And what is more interesting, even more interesting, is that if you look at the light data, right? The light data, where is that from? From the data, right? From data. So data is definitely received by what? By the SPI module. So you want to look at the SPI receiver here. SPI receiver. SPI receiver is 8 bits data length, but your top overrides it to 16. So see, remember we have a hashtag and then parentheses. You can overwrite whatever the first parameter is following a certain order. If it doesn't have other parameters, this will overwrite the first parameter in your sum module. So if you go to our SPI leader receiver module, you can see the first parameter is what? This guy. So this will be overrated. As we said, SPI's data length is customizable. You can always change it. We define it as 8 over here. We can always change it at the top. So this is how we change it, right? So we overwrite it. It's gonna count until the 16th bit, and then stop taking more data bits into it. So why do we need a 16 bits? It's only 8-bit data, right? ADC is only giving us 8 bits resolution. Why we are taking 16 bits? So there isn't an answer to answer these questions scientifically or technically. I read it from the ADC data sheet. It just tells you that it's going to output a pattern. I'm going to write it down here. So ADC output, okay? That's from the data sheet. Whoever designed, the engineer from TI, Texas Instrument, they designed ADC. They designed it that way. So what's happening is you got a 4 trailing zeros at the very beginning from the LSP. And then you have your 8-bit data. That's the data. And then there will be 3 leading zeros for some reason. And if something happens, I think they were talking about the timing of the SPI. If the chip enable happens before the clock for some reason, I don't know why, but there might be a reason that if the user accidentally make that happen, which is SS happens before the clock, right? They should be aligned. It should be synchronized. But just in case this happens before it, and it's going to generate an extra 0 here, and making it 4 leading zeros for the data, the message to be sent out as a converted output. And I don't know why, but the thing is, you're going to expect 4 trailing zeros and 4 leading zeros, sometimes 3 leading zeros. In the middle, you have 8 bits data in the middle. So just in case it becomes 16 bits, right? I just use my SPI to receive 16 bits. And I don't need all these bits. Doesn't matter. I don't even care if there's a 0 here. I just don't care. So I'm not using it. But I do have this capability to receive 16 bits. And then only take out these 8 bits as a data. Right? We don't know why they designed it that way. The ADC is just doing it. Okay? So that's the output of the ADC. It's probably providing a little bit buffering area front and at the rear and the front as well. So just in case it's not ready, you still have a something to lose, right? It's not losing any information. So now, what is this bit? It's bit what? Bit 5. Oh, it's actually bit 4. Is it? Yeah, it's actually bit 4. 0, 1, 2, 3. It's a bit 4. So if this is bit 4, this becomes a problem though. So it's question number 3 in class number 11. It asks you the LSB of the ADC digitized output starts at which bit of the output. It actually should be bit 4, right? Should be bit 4. It's the 5th bit from the right, but should be bit 4. So for this code here, by doing this, you are, I don't know, interesting. If I overexpose it, I use my flashlight to actually shine on the light sensor. I'm reading 255 actually. I'm reading 255.
Shouldn't that be 11 to 4?
That's what I'm thinking, right? So because the ADC does say that it starts from the 5th bit, which is bit 4. I see. I have that over here. No ADC. See, this is directly copy and pasted from the ADC. So the ADC produces 3 leading zeros bits, followed by 8 data bits, and most significant first. And then after the data bits, the ADC clocks out 4 trailing zeros. Right? So it's 4 trailing zeros, not 5. So it's 4 trailing zeros, and then the 5th bit should be the LSB, because that's data is being put in there. Doesn't match the theory though, but I did read 255 by using this code. Okay, let's just use it. Just use this code for now. If you want to try it, just test it from 4 to 11 and see what's going to happen. I believe it will be up to what? You got a 0 and 7 ones, right? So it's going to be 254. You know what I mean? Let me draw it for you. So if you are getting, so for example, you shine a very strong light to the light sensor, and these ones are all ones, right? All ones. 8 bits, right? All ones. Since I'm taking 5 to 12, so it should be up to 125 actually. 128, 127. Is it 7 ones and 1 0? 0 and 7 ones. Is that 127? It's 127, right? So I shouldn't read 255. Let's try it. I mean, I'm going to try it after the class and see what happens.
Right?
Hmm?
7 ones.
Wait.
2 to 7.
No. 7 ones is 127. Because 2 to the 7th is 126, right? 2 to the 8th is 256.
It's 128.
128.
So then if you have 7 ones, then you have another 6 ones that give you 127.
No, because
Wait, yeah, because you're.
yeah.
This one's
Because this guy is a 7th, right? Here, and you have 6 zeros. No. 7 zeros. Yeah, let's try it. Try it later and see how that works. Okay, but this one does give you good results, unless the data sheet of the ADC is inaccurate. But anyway, so we know some of the tricks over here. It's just the ADC is outputting a certain pattern of data like this. So one way to look at it is actually we can throw the entire 16 bits to all the 16 channels, the oscilloscope. It has a digital data input. You can just look at all the bits, right? So that's another way to monitor it. Anyway, let's see other questions on the in class. Number 4, right? Number 4. Which mode is this operating at?
Leader receiver.
No, I mean the SPI mode.
Oh.
So SPI has different modes, right? Has 4 modes. Has mode 0, 1, 2, 3, right? Mode 1, 2, 3. I'll just draw on the paper. That's easier. So by looking at the description of it, see, just read this paragraph. This is directly copy and pasted from the official website. So there's a little follower transmitter module in the PMOD sensor, right? Because the follower is the transmitter, so it has a follower transmitter SPI module in there, and in the ADC. So if it's doing SPI communication, it needs to follow one of the modes, like this. Okay. If you follow one of the modes, your leader receiver need to be programmed or being designed in the same mode. Otherwise, they are not going to communicate. That makes sense? So we have to know what is actually happening here. So by reading this one, we should be able to figure out, okay? So the PMOD, this sensor, right? This sensor. So frequency first, 1 MHz to 4 MHz. So your SPI have to provide the clock SDK to be, the frequency has to fall into this range. So the first question is it falling into this range or not? By counting up to 25. What's the frequency of SDK? How do we calculate it? Remember? So it flips every 25 cycles, right? So how many cycles per period? 50. 50 counts. It's counting at 100 megahertz, so 100 mega counts per second. Right? We got 50 counts, right? 50 counts. So divided by 50 counts. So this becomes 2 mega periods per second, or 2 megahertz. So it requires 1 to 4, and we are getting 2, which is great. And the bits of information placed on the falling edge of the clock. So by following this one, you can see it's been placed. It's been placed, which means the falling edge of the SDK will update your data. So it's right at the very beginning of every data, right? So falling edge of the SDK should make this guy available. And the rising edge of the SDK it says will valid on the subsequent rising edge. So which means valid means it will be taken in, right? Will be taken in, will be sampled. So it should sample in the middle. So the previous falling edge update will place the data here, it makes it available, so data starts coming in. And the subsequent rising edge will sample it right in the middle of the data. So you should draw it, so this should happen this way. And then until the next falling edge, it updates the data, places the new data here, and then the subsequent rising edge will sample it. So just keep going like this. However, it has to be enabled before that, right? So that is why the previous rising edge will enable it. Okay? The rising edge enables it. Okay? So, just by looking at this one, let's do a snapshot. We look at the ADCs. So this description over here comes from the ADC. So this is the ADC's SPI operating mode, right? So we just talk about it, and then we convert it into this timing gram from the ADC's SPI, right? And now we scroll up to the 4 modes here. By looking at this guy, could you tell me which one is actually being used for the ADC? Which one? So CPOL and CPHA should be what? Wait, so rising edge enables it, right? So there's no rising edge, but it didn't draw it, but you can imagine here should be a rising edge, right? There should be a rising edge over here. That rising edge enables it. Not falling edge enabled it. So CPOL has to be what? 1. Okay? And then the falling edge should what? The next falling edge after the enable rising edge, the next falling edge should do what? Should place the data to the data line, right? Which one placed it to the data line? This one? These ones? No, these ones in the middle, just sampling it, right? So these ones, right? These ones. So CPHA has to be what? 1. And now let's check the subsequent rising edge, see if it's sampling it. Right? This one updates it, and this one right in the middle samples it. Okay? So exactly whatever we saw from the ADC. So CPOL and CPHA, this is a typo here. So CPHA, so the phase and polarity should be 1, 1. So 1, 1 is what? Mode what? No, mode 3. So it's from 0, 0, 0, 1, 1, 0, 1, 1, right? So the 3 will be mode 3. Mode 3. So it's running at mode 3, and just perfectly is whatever the textbook's SPI leader receiver is programmed as. Okay, so this guy is exactly mode 3. Is that because we're just lucky? Nope, because the textbook just looking at their operating mode and programmed it that way. Okay, so we can directly plug in and use it. And now let's check this really quickly and see if this is exactly mode 3. So remember the rising edge of that CK, exactly the first one, right? The first rising edge of that CK will do what? Will enable it, right? See, rising edge of that CK enables it. So the first rising edge of that CK enables it, but does it do anything else? Rising edge enables it. Does it do anything else? No, the data is not available yet. So you're getting high impedance. So Z, high impedance, nothing. See if that's the case. Nothing. I'm not doing anything. I'm just updating. I'm just asserting the flags and making the index ready, but nothing else. I didn't do anything, right? So until the next rising edge arrives, so between 2 rising edges, what do we have in the middle? A falling edge. One rising edge, you definitely have a falling edge in the middle, right? And the falling edge will do what? Will place the data to the data line, and which is not, you don't have to program it over here. Why? Why you don't have to program it over here, the falling edge stuff? Let me start over again, okay? So this is the leader receiver, and has the rising edge and falling edges being defined by the leader receiver, because I programmed it that way, as IPGA is being hard coded into it. And it's a leader, so I enables it, because the leader is in charge of enabling things and in charge of sending out clocks. So the first rising edge, the very first rising edge of the clock enables it. That makes sense, because this is what we are supposed to do. Rising edge enables it. Okay? So which is enabled? Which is enabled? The follower. The follower is enabled. So there's a little SPI module, which is the follower transmitter module inside the light sensor module, the ADC. We'll look at this pin, and only when this is 0, it will place the data to the data line at which edge? At which edge? At which edge? Huh? Which one? The following edge here. The two devices are being synchronized by the same clock. You agree with that? If this clock is doing something, the follower will see it, right? So rising edge, so now the leader is doing it. The rising edge is hard coded in here. The rising edge will enable it, the first one, right? The first one will enable it. So SS goes down, right? It enables it, right? And then keep going. Okay, keep going. Because the ICK will have a falling edge right after it, right? So the ICK has a falling edge. So that falling edge will be seen by the follower. And the follower has an SPI follower transmitter module inside, is detecting that falling edge, is doing what? Always at negative edge of the SDK, right? And then getting to their state machine and checking, hey, falling edge comes, I still want to see if the chip select is low. Is the chip select low? Yes, because see, it's already enabled, it's low. So the follower transmitter is seeing this condition satisfied, so it's going to do what? Falling edge, and also the chip select is low. What the follower transmitter is going to do in the ADC? It's going to place the data over here, right? It's going to place the data over here to the data line, and it does it. So the falling edge will place the data over here. So data appears at the line, which is SDO line. So the data output, the serial data output, SDO, right? SDO line will have the data from the data center from the ADC. Over here, there will be a 1 bit available. And the subsequent rising edge of the SDK comes from the leader. Will do what? See, it's going to be here. It's this state, right? It goes to the next state already, because the first rising edge already done. So it's moved to the next state. So this state will take the data in from missile, right? Or SDO. See, this is being sampled. It's being sampled. And this is being sampled at this point, right in the middle of the data. It's over here. How do we make sure that it's sampled in the middle? Why it looks like it's in the middle? Yeah, the rising edge samples in the middle, right? Why it looks like it's in the middle of the data? Because the next falling edge just updated, right? So the rising edge is right in the middle of the two falling edges. And the falling edges will update the data. So that's why the rising edge in the middle will sample the data in the middle. Since the falling edge will change it, right? So the falling edges will change it. That answers one of the questions, right? I hope. Where we are at right now. Question number 3, 4, done. This is where we're talking about the molds. Number 5. When SS is put down, because so SS is put down at the first rising edge of the SDK, right? And it has to be synchronized. And when is the first data made available by PMOD? It's the first falling edge after the first rising edge of the SEK. So subsequent falling edge of the first rising edge of the SEK. When is the first data being sampled by the SPI inside the IPGA? When is the first data being sampled? That's the second rising edge, right? Second rising edge of the SEK. All right. So one more last thing for question number 8. We answered the first half already, and for the second half, what is the sampling rate of the SPI? What is sampling rate of the SPI? So you are thinking, hey, the SPI is sampling at 2 megahertz, and it takes 16 clocks. No, sorry. SDK is running at 2 megahertz and takes 16 SDK cycles to finish one sample. So you are thinking the sample per second seems to be 2 megahertz divided by 16. So you are expecting what? $2 million divided by 16. So expecting 125,000 samples per second, and that is not right. Why is that? If you look at the code, it's not running at full speed. See what's happening? It set up a counter and set up a delay time, a parameter called 500, and 500 times 2,000, just making the number bigger for some reason. I think this one is, you can override it, right? But this one is not, you cannot override it. So you can change this parameter here to change the delay time. But anyway, so for this example, the total number of counts becomes 500 times 2,000, which is what? 1 million. It's 1 million. And it's actually looking at the delay. So delay has to be 0 in order to enable it. Otherwise, delay just keeps subtracting 1. So they actually have a max count, which is 1 million. Right? It's 1 million. So it only enables the SPI conversion because you can see get is 1, so it's a flag. It's being used for the SPI receiver, little receiver mode. See, there's a get, which is a flag. So it has to be 1 in order to enable it. So in that case, it actually wouldn't enable as SPI every 1 million counts. Okay? So in that case, how many samples would you expect every second will be sampled every second? How many samples would be actually received every single second? We have a 100 megahertz. Oh no, sorry, 2 megahertz clock. Right, it's 2 megahertz. And that 2 megahertz clock counts up to 2, so which means it's able to count 2 million times a second, and it only sample 1 SPI or collect 1 SPI or do 1 SPI communication every 1 million counts. So how many samples you are getting per second? 2. It's counting 2 million counts every second, right? And only do 1 SPI enable per 1 million counts. Yes, it takes 16 cycles to finish it, but that's pretty fast. I don't really care. It's only 16 counts out of 2 million hertz of SEK. I can ignore it. Let me draw it for you guys. 0 to 1 second. Okay? How many counts? 2 million. Once it reaches 1 million, it do what? Sample SPI. How long it takes? How long it takes? This much? 16 cycles. I couldn't even draw it. So that's 16 cycles times what? Is it a long time? Compared to 1 second? No. So I have to, it's probably just one line here. Do I care? No. So in 1 second, how many samples you are collecting? 2. Probably like 1.0001 second. You are getting 2 samples. Okay? I don't know. It's just estimate. Probably. Could be less. So it's about 1 second. Every second you are getting 2 samples, right? For this application. Do you need more samples every second for this application? You are detecting what? Ambient light. You care about that much about ambient light changing every second? Why not?
I mean,
Oh, you
depends on
don't.
your application, probably not.
Ambient light, you probably don't, right? But what are the applications you really care about for light signal? Gavin knows. The DDPs are droplets, pulses, optic fibers, right? Instantaneous, just very fast light pulses, right? Like signal comes from whatever biosignals or from droplet sorter. So what we designed in the research projects, we are running a micro channel. This is about let's say 100 micron, right? Micrometers, and we are running droplets, and some of the droplets has fluorescence in it, right? And then we have an optic detector over here, just detecting it, right? Just detecting optic detector. And we run the droplets through this channel really quickly at 2000 hertz, for example. So which means 2000 droplets are going through this detector every second. It's really fast. So the droplets are running really fast that way. So whenever there's a positive droplet shows up, it's gonna show you a pulse, right? In that case, definitely you want to increase the frequency, the sampling frequency of this application. This is changing really fast. 2K hertz, right? Okay. So that's the last question. Let's look at in class number 10. I will let you guys go earlier, like 5 minutes earlier. This is spring break. Number 12, we answered it. Right? Did we answer number 12 of in class number 10? Is SPI licensor.v. What is that overriding? And you know it. And how many bits from the light data is used? And that's it. Okay, one quick comment on the tasks over here. Then we'll let you go. Okay, 2 tasks for this tutorial. First one, just repeat it. Repeat whatever I demoed in the video over here. And the second one is called a smart light controller. So if the light is strong, you dim it. If the light is weak, the ambient light is weak, you make it stronger. So we don't have a PWM. So what I will let you guys to do is, we have 16 LEDs, right? You have 16 LEDs. And assuming that there's no feedback. So you use your hand to give a more or less light to the light sensor. You can hide it, you can just fully expose it. And if you make it darker, like cover it totally, all the 16 LEDs should be on. Try to make the environment more brighter. Actually, it doesn't because there are little LED, green LEDs. It's not doing anything. But just assuming that they are bright light bulbs, right? So it's actually fully turned on. All 16 LEDs are fully turned on. Try to make the environment brighter. But it's not giving a feedback. Use your hand to change the ambient light intensity. Okay, and then if you move your hand aside, and so the light sensor is fully exposed, it should show no LEDs. And if you cover a little bit, it starts showing more LEDs. It's basically you are seeing the LEDs being turned on in a pattern like this, okay, from 0 to all of them, based on the light being received by the light sensor. And that has to be coded in the software as assembly, so which means you have to use a Pico Blaze. For condition, so you are doing some comparison and jumps to get it done. And you're asking, we can also implement it using hardware. Why we are not doing it? Why we just don't do it? I mean, Verilog, you can do if, right? So if that's larger, we do this, right? So why we are not directly implementing everything in Verilog? What's the difference? Using software and hardware, what's the difference? If you implement it as a hardware, assuming that this is being taped out by a foundry, it becomes a chip. Can you still change it? That's the whole point, right? So we can use the software to change that threshold by just coding it up. We can change the threshold. We could totally disable it, or we can change the threshold based on the light intensity and how many lights we're gonna turn on based on the brightness, right? So this becomes customizable hardware instead of hard-coded fabricated hardware. Even though we can definitely reprogram the IPGA, but assuming if this is SoC, is a chip, then no one can further change it if it's being fabricated. The same concept. And I think that's why 60 years ago people started inventing programmable chips and eventually become microcontrollers, since you can customize whatever you want the hardware to do by reprogram the software instead of hard code everything into the hardware. Okay? Questions, anything? Okay. See you after the break.